All right, guys. So this section, section 15.4, is about segment relationships in circles. Okay, so for our learning target here, I can solve problems that use properties of chords. Okay, so we're mostly dealing with segments within circles. The first theorem we're going to look at is the chord product theorem. So if I have two chords and they intersect in the interior of a circle, like this one here, chord AB intersects chord CD at point E, right? Then I know that the products of the lengths of the segments of the chords are going to be equal. So here I have AE times EB, okay? That product is going to be equal to CE times ED, okay? So that's the chord product theorem. Let's look at an example at how you can use that. So here I have this circle and I have this chord AB and this chord CD. I know that CE is X, ED is 8, AE is 6, and EB is 5, and I'm looking for X, okay? So I set up the products, okay, of the segments. CE times ED equals AE times EB, okay? That's my first statement right here. And then I just substitute. Okay, CE is X, ED is 8, AE is 6, and then EB is 5. Okay, so now I do 8x equals 6 times 5, 30, divide by 8, and I get x equals 3.75. Okay, so now it also says to find the length of each chord. Okay, well, I know that AB is just 6 plus 5. Okay, so that's 11. And I know that CD is x plus 8. So x is 3.75 plus 8. It gives me 11.75. Okay. All right, so the next one is a little bit self-intuitive. We're using chords of a circle, okay? So if I have two arcs of one circle, if they have the same measure, then they're congruent, okay? Congruent arcs also have the same length, okay? So for example, here, arc AB and arc CD, okay? They are congruent, they're both 75, okay? Then here I have this example here. Well, I know that this arc YX and ZW are congruent because of the little dash tick mark right there. So since ZW is 23, I know that YX is also 23. Okay. And the other thing that has to do with chords and the arc of the chord, right, is this idea that, okay, if I have a chord, okay, and I have a minor arc that has the same endpoints as the chord, okay, so that arc is called arc of the chord. Okay, so arc EF is the arc of the chord EF. Okay, this is just some like vocabulary and definitions, okay, for you to keep in mind. Okay, now we have what's called arc chord theorem. Okay, so the arc chord theorem says that in a circle or in congruent circles, two minor arcs are congruent if and only if, okay, their corresponding chords are congruent. So here I have this chord EF, and I have this chord AB, okay? Because those two chords are congruent, I know that the arc AB is congruent to arc EF, okay? So it goes back and forth both ways. If I know the arcs are congruent, so the corresponding chords are going to be congruent. Or if I start off with the fact that the chords are congruent, then I know the intercepted arcs, right? The arc of those chords are going to have to be congruent as well, okay? So let's look at this example here. Here I have this circle with what it looks like two triangles, right? Inscribed in the circle. here I have this angle ECD and angle ACB. These two angles are the same, right? They're congruent because of the angle marking right there. So because the angles are congruent, I know that the intercepted arcs to those central angles are also going to be congruent. So I know ED is going to be congruent to arc AB, right? Because of the central angles being the same, okay? And because those arcs are congruent, I know that chord AB and chord ED are also going to be congruent. Okay, so in order for me to find what X is, I know that that's going to be the same length as this chord that measures 4. Okay, so I know X is going to be equal to 4. So I go from central angle to intercepted arcs, from intercepted arcs to the corresponding chords, okay, of those arcs. Let's look at the second one. The second one, I start off with these two triangles that are right triangles, right? I have this 90-degree angle. So because this angle HJG is 90 degrees, I also know that angle FJG has to be 90 degrees, right? Because this is the diameter. I can see that this is the diameter. It forms a line. So that means this whole angle has to be 180 degrees, which makes each one of them 90 degrees, okay? So now because this is 90 degrees, HG is also going to be 90 degrees, and GF is also going to be 90 degrees because of this central angle. Now, because those chords, because the arcs of those chords are congruent, I know that the chords are also going to be congruent. So now I just do X plus 2 equals 5. And when I solve this, I subtract 2 from both sides and I get X equals 3. Okay. The third one is about the same idea, but now I'm going from the outside in. So look, I have the chords, I have the tick mark telling me that ZY, chord ZY is congruent to chord VU. Because those chords are congruent, I know that the arc of those chords are going to be congruent. So arc VU and arc YZ are also congruent. Okay, because those arcs are congruent, I know that the central angles that corresponds to those arcs are congruent. So this angle right here is going to be congruent to this angle right here. Okay, VWU is going to be congruent to YWZ. And now I just set up the expressions. X plus 10 equals 40. Subtract 10 from both sides, and I get X equals 30. All right, so now let's look at the diameter chord theorem. If I have a diameter and that diameter is perpendicular to a chord, okay, then the diameter bisects the chord and its arc. So here we go. I have diameter BG, and I know that BG is perpendicular to DF, which is a chord. Okay. Now, because they are perpendicular, I know that the segment here DE, okay, is going to be congruent to segment EF, okay, because the diameter cuts the chord in half, okay, in 2 equal parts. Now, because those chords are, because that chord is split in half, the arc of that chord is also going to be split in half. So that means that arc DG is going to be congruent to arc GF. Okay. So let's see an example. Here I have, is asking me to find the length of JM. Okay, JM is this, it's the segment here that makes the chord HJ. So I know GK is the diameter because it goes through the center and it goes from one end to the other of the circle. So I know that's the diameter. I know that the diameter right here cuts this chord in a 90-degree angle. I have this little box. So now because that's 90 degrees, I know that HM is going to be equal to MJ. Okay, the diameter is gonna cut this chord into equal parts. So because HM is 12, I know that MJ is also going to be 12. All right, now we have the perpendicular bisector chord theorem. So now I have, if one chord is a perpendicular bisector of another chord, then the first chord is a diameter, okay? You can't have two chords being perpendicular without one of them being the diameter, okay? So this is kind of like looking at the previous theorem, and it's just going the other way, okay? And going backwards. You can conclude that one of the chords is going to be the diameter, okay? Since those two chords cross at a 90-degree angle, okay? Let's look at this example here. Well, find the length of the radius of a circle if a chord is 10 inches long and 12 inches from the center, okay? So here I have this chord, okay? And I have the radius, okay? This radius right here. I know the radius is going to be, the chord is 10 inches, okay? And I know that the radius is half of the diameter, right? It's half of the diameter. So I know that this line here is where the diameter would go, okay? I know that the radius is cutting the chord at a 90-degree angle right here, okay? So that means that this radius is cutting the chord in half, okay, into equal parts. So that's why I know that AB here is 10. So I know that each side is going to be 5 here of the chord, okay? Now I have that the radius. So find the length of the radius of a circle if a chord is 10 inches long and 12 inches from the center. Okay, so the chord is 12 inches from the center. So that's why I label this piece right here 12. Okay. So now I'm just going to use Pythagorean theorem to find C right here. Okay, so I drew this little 90, I drew this little right triangle, and I'm going to find AP. AP is going to be the radius, okay, the length of the radius. So I did C squared equals 12 squared plus 5 squared. C squared equals 144 plus 25. C squared equals 169. Square root both sides, I get C equals plus or minus 13, okay? And so remember, every time you take the square root, you have two answers, a negative and a positive. But because we're talking about a distance, right? Radius is a distance. That value cannot be negative. So I'm going to disregard the negative, and my answer is the radius is 13. Right, so now the last theorem, right? Chord to center theorem. In a circle or congruent circles, two chords are congruent if and only if they are equidistant from the center. Okay, so notice here that chord GF and chord DC, right? They are the same distance from the center. See right here, the segment EA has a tick mark, and the segment AW also has a tick mark. So that means that this chord DC and this chord GF are the same distance from the center of the circle. Okay, so because they are the same distance from the center, that means they're going to be congruent. Okay, chords are congruent if they are equidistant from the center, And they are also congruent if their arcs are the same size, okay? So the chords are going to be congruent if they're the same distance from the center, and also, like we saw above, they're also going to be congruent if their arcs are congruent, okay, or have the same size.